time graphs, we found out that they have a varied variety. They come in different varieties, shapes, and forms, all telling us different outcomes of the object that they are representing is straight line motion. Are we clear? Oh, let me do this again. Small that. All right. Mm-hmm. Now wait for you. All right. So there, the displacement time graph, also called a position time graph, because obviously with displacement you can determine the position or location of object. Are we clear? As per where it was and where it ended up per unit time. In what not per unit time, in whatever direction. Are we clear? So here we have, hopefully everybody joined the book already. We have position time. Position time, position time, position time. Each of these are displacement versus time graphs. Are we clear on that? However, if you see a displacement time graph, we have a flat line, completely flat. It is at rest. Are we clear? Because you now cover no new distance. Am I clear? Are we clear? So as long as time of progress are going from 1 go down a 5 hour, you now move from your position or your location. Are we clear? You now move. If you see a graph with a slope to the right hand, it is basically speeding up. No, me never second, no say acceleration just yet. Are we clear? It is speeding up. Are we clear? If the slope is downward, it is deceleration really and truly. You're losing speed. You're slowing down. Look where it start from. Him start basically at a higher range up here, and over time he reduced. Are we clear? So please appreciate the fact him still a cover distance, and him a cover distance in a unit time, but he's doing it in the opposite direction. So really and truly, it means that he is slowing down. Acceleration is but with a negative sign. So acceleration versus retardation. Now here we see a one with a parabolic kind of design, a curved line of best fit. Are we clear? So if you see a curved line of curve of best fit, this is actually what is showing acceleration. None of them are not show acceleration or deceleration. I was saying they are speed up or slow down. Are we clear? Acceleration are change in a velocity. Each of these, you don't really have a change. It'll be a constant. This is over one or so. So this is constant accelerate, constant speed, right? Constant slowing down. Because every minute, if you put 1 minute, there's so 2 minutes, 3 minutes, 4 minutes, at each interval, you must slow down by the same value. Are we clear? Must cover distance by the same value. So it's constant. You don't really have no changes. So you get to where I come from? However, you come over here so now. Look at the differences. 1 minute, 2 minutes, 3 minutes, 4 minutes, 5 minutes. Going across, plotting over back to the x-axis, you find out, say, at each interval, you must cover different amount of distance. Am I clear? You must cover different amount of distance at each time interval. Are we clear? And for that, because each distance covered is different, because of curve you are dealing with that straight line, you have to appreciate the fact that it is accelerating. The velocity is changing at the different time period. Am I clear? If at the same distance you are cover, over here so, a constant business you are dealing with. Are we clear? Constant speed. If you have a curve, you now will get no same distance covered per unit time because the curve is warped, it bent. Are we clear? So if you try to extrapolate or pull from it, you now get the same value at any given time. Everybody draw this in the name book. Everybody have this? All right, good. Now the next thing. The steeper the slope, the higher the speed. The steeper the slope, the higher the speed. So if we had a slope like this, we're steep so, it has to be appreciated that object A has to be traveling faster than object B. Am I clear? Because theme slope is a steeper one. Am I clear on that? All right, good. Now, continuing, we have some other variations of them around here. So, Again, the same terms where you buy so where you say basically object at rest, see it there again. Are we clear? If you want to see uniform velocity, see it there again. I same thing. Accelerating, see it there again. Decelerating, that is it. You get how deceleration look now? So it basically is a curve on a displacement time graph. You get the message? In the with a negative value, right? So please appreciate that. So I think we don't have this and this already, no so. That one of the runners, so this is a uniform velocity. Slope is positive, velocity is constant slash uniform. That this right there, so put constant slash uniform. So you don't have to try it over again. This one right here, put constant, the velocity is constant slash uniform. Catch a uniform somewhere because constant and uniform mean the same thing. Look at what I wrote on the board. Remember that, look at the words in red. Remember that the words uniform, constant, and steady mean the same thing in a kinematics. Are we clear? Constant, uniform, and steady mean the same thing. Don't make your examiner take you by surprise. Are we clear? So if you have that, all you need to do, I just draw. Well, if you draw that already, all you need to do, I draw that. That's all. That's all. We draw that already. Just that one you need to draw. Are we clear or not? What does the gradient of a velocity time graph give? What does the gradient of a displacement time graph give? Can't give speed because speed not deal nothing with direction. Velocity. Are we clear on that? No. Write this please. The gradient of a displacement time graph gives velocity. You can write that under it. The gradient of a displacement time graph gives velocity. The gradient of a displacement y2 from y1 over x2 from x1 business, it will give you velocity. Why, you might ask? Well, it is evident. You have displacement on an axis, and it's going to be divided by time. Are we clear? I will use y2 for y1, x2 for x1 also. So your displacement values is always going to be the y1 values and y2 values. And it's going to be divided by the x2 and x1 values, which always will be time. So you will have displacement over time. That is velocity. Am I clear on that? For velocity always have a direction component. The next day you have your clothes, you put in a that's here. Are we finished? Are we done? One line I can't that hard, I can't complicate it. Are we done? We finished? Good. So here we have a nice graph. This graph shows a journey of 2,000 meters. It includes a stop of 1 hour after traveling 1,000 meters. The person then returns to their starting position. Well, go on this one. How you determine that? Number one, where part show the 1 hour stop? 20 to 80. So all of this region up here, that's flat. This is a region where it was at rest. Am I clear? In a cover new distance. In a 10 minutes, in covered 400 meters. Are we clear? In a 20 minutes, he covered 1,000 meters. You get me? From 20 door to 80, did he reach climb any higher distance? Eh? No, he just flatline so no. It's not like he go up there so. And like he basically have a plateau person now. And we call that 1,200 or not. You get where I come from? He never climb no higher. He just flatline so. And then now what does he start to do? Decelerate. And because he touch back the same x-axis when start from, you say he return to his starting position. Everybody get that? As a x he start from the origin, and he eventually came back to the origin. Are we clear on that? So on these graphs, it can tell you also when you have returned to your starting position. Are we clear? Sketch this off now. Not have to be pretty. Don't have to be pretty at all. Just make sure say at least your graph agree with the 20 to 80. Are we clear? Are we clear on that? Are we finished? Can I go now? We're gonna look on the calculation them each. So number one, we after we do what we are do, after we draw everything, we plot the graph and we draw the line in up best we go up, we draw one, go so we draw one, come down. We want to calculate the gradient. Are we clear? So for example, for the first part of the journey, the gradient of this graph is velocity. So let's say determine the velocity. Write this question, determine the velocity. Determine the velocity for the first 20 minutes. For first 20 minutes. 20 min. And for the time duration of 80 to 100. Are you clear? 80 to 100. Are you clear on that? Hmm? Where? Here? Determine the velocity for the first 20 minutes. And for the time duration, for the time duration for the time duration of 80 to 100 minutes. Are you ready? Oh no, wait. 80 to 110, my apology. 80 to 110. Or we could have said when the objects start move again. Are we clear? Which I mean it 80 to 110. All right. Ready? Are you ready? Must can move you know. I don't know but pay attention. Don't do no maths. Pay attention. I'll record for us. For the first part of the journey, between 20 to 80, 0 to 20, what distance did he cover? 1000 meter. All right. So find the gradient, big triangle. All right. Big triangle, carry him down, carry him across. You don't know, say, your y2 value is going to be what? So for this one, your y2 from y1 over x2. Good. So, good. So basically, I will get 0 down here, so for your y1 and 1000 plus for your y2. So basically, that is equivalent to 1000 from 0 all over what? 20 from 0. Are you clear? 20 from 0. Which I'm going to give it 1000 divided by 20. Are we clear? 20 goes into 1500 times. 500 times. 50. 50. 50 times. That makes sense. Now, having done that, we basically appreciate something. The unit is going to be everything over here, so I'm going to be in a meter. Everything on the bottom is going to be in minutes. Because a minutes, well, a minutes we are do for this one. We could have had meters, we could have had seconds down here, but this graph is a graph of displacement in meters versus time in minutes. Are we clear? Which is more rational for the world per se. That we measure in a second. But anyway, so meters per minute. Are we clear? That would be it for that. For the second part of the graph, when this car start move again, he actually he started to decelerate. Are we clear? Not really decelerate, but slow down. Are we clear? Because we can't say decelerate here because we not deal with acceleration per se. Are we clear? There is no change. You must cover the same amount of distance per unit time. So it's constant. And so your velocity not change. So therefore, appreciate something about this. What is different about this region versus that region? Or this slope versus this slope? What's the difference between them? Good. Good. So when you find your y2 and y1 value, you shall make it negative. Are we clear? So again, it is 0 subtracted from 1000. Are we clear? However, you have to at this time make the 1000 negative. If you don't do that, you get now. Are we clear? As a negative slope. So whatever value you get, you must appreciate that it's a negative slope. So make it negative and 80, and here's 100. Wait up, so 110, right? So that's my y1 value, but this is my x1 value. This is my x2 value, and therefore, so we have 0, negative 0. Just make everything negative. I bracket. I'll just make it negative afterwards. 1000 for 0 all over 1110 for 30. Right? Make you all like 0, make you all like negative, and you get your answer. Are we clear? So you have 1000 divided by 30. How much you get? 33.33, and that is a negative. And when we say negative, we don't mean say it's a negative value per se. We mean that it shows say in this say it's slowing down. Are we clear? So negative 33.33, and again meters per minute. Meters per minute. Everybody have that? So you can bracket and make it like negative if you want. That floats my boat. And then eventually your answer is going to be negative. Are we clear on that? Are we ready? Just because it is this region that is decelerating, I do not have to do no negative nothing because I want a positive slope. Are we clear? One that goes up positive, one that goes down negative. Are we clear? Can we move ahead now? So now we move on to our next graph. Velocity time graph. So now we have a brand new graph, velocity time graph, and we'll also be looking at speed time graphs. So one must be able to interpret what is happening at different levels of a velocity versus time graph. Are we clear? So a velocity time graph, you have velocity on the y-axis and you have time on the x-axis. Are we clear? Are we clear? Remember, say velocity is distance covered in a given direction per unit time. So you understand where I come from? So a displacement component, by virtue of saying velocity, is already taken care of. All that you are focusing on now is the velocity itself. You already established that you have direction. Are we clear? Are we clear? So watch me now. If you see a graph, a velocity versus time graph, you look on the graph and you see velocity on the x, on the y. You look on x and you see time. You are sure that's a velocity time graph. If you see a flat line like that and anywhere on it, what does that mean? Velocity? No, sir. No, sir. Constant velocity. You do not have distance again on the y-axis. You know where I come from? So you can't say that a flat line again means in a move. I want to forget where I come from. The only reason why flat line means in a move over here so because distance or displacement was on the two previous graphs what you do. You get where I come from? So you could have said this thing now cover no new distance along the y-axis. Am I clear? So do you see distance? No. So all of this thing, meaning say as time progress, 1 minute, let me tell you what this area do. 1 minute, well, let's say 10 second, 20 second, yeah man, 30 second. At each of these second interval, let's say 5, 10, 15, 20 meter per second. All along this time interval, as time progress, what? As time progress, the velocity stays the same. So if flow the input is like input on the gas. And we are not considering friction for the tire if slow not down. Are you clear? Like a perfect frictional environment. So I'm putting foot down on the gas and he never really moving foot. Are you clear? We are also going to cancel out the possibility that there would have been air drag. Are you clear? So perfectly frictional, dragless environment. He puts his foot on the gas pedal and he never moves it from that position. He never take it up, neither did he press it down hard. Are you clear? So he on the speedometer, he makes sure say on the speedometer in the car, like he stopped at 20, the arrow there at 20 and he never really move. Am I clear? Are we clear? Constant velocity. Am I clear on that? No. Suppose if me see a slope like that. What that mean? A slope like that. Perfectly from the origin go. What that mean? Why constant acceleration? And what that mean is in terms of acceleration? What do you mean speed up? Eh? Little by little at what would you say? Hmm? You remember that little thing, that little car that we look from the past point A, point B? Won't appreciate from that. It is go. You get where I come from. So in a 1 minute, it might increase by 4 meters per second per velocity. Second minute, same 4 meters per second velocity. Third minute, same 4 meters per second velocity. Are you clear? So if that is the case, his velocity is changing at equal values. And so we say that the acceleration is constant because the velocity has changed. Yes, but it not change at unequal value like 4, then 8, then 16, then 20. You get where I come from? A 4, it changed by equivalent values of 4 in that example around back there, right? So, first minute, second minute, or seconds, whatever, third minute, 10, 20, 30, 40, whatever. Equal time interval as best as me can try freehand. You get where I come from? So you find out if you have a case like this and now where 3 shoot up, gone now and gone up, so would that be constant again? No, because it's a different, like say you would that be from 10 from 20 at 10, but from 20 to 40 at 20. You get where I come from? So, is it in flow the gas when you reach the third minute? Are you clear? So appreciate that such a graph like this, if not if drawn at not at hand like when we draw it, you see it like this, it means velocity have to depend on why no people. So therefore you learn something today. If you are going to approach these graphs with sense, you must appreciate what values are written on each of their axes. Because when you determine is it a speed is it a distance versus time graph? Is it a displacement versus time graph? Is it a velocity versus time graph? When you know what kind of graph it be, then how the graph look can be determined by you. Am I clear? If you don't know what kind of graph it be, you're going to make a mistake like how them make. Them see a flat line and say, yo, I must move the car now, move the car is moving. The car will cover distance, sir. Are we clear on that? Because we never see displacement funny. Are we clear? Are we clear? Appreciate velocity is this displacement versus time. No. Don't ask what this mean. What this mean? A velocity versus time graph. No, what's up? Constant deceleration. So he is now slowing down at every second in what? Equal amount. So is he then lose 4 meters per second at the first second, lose another 4 at the second, lose another 4 in the third second. Are we clear? You get that? And what about this one? I love that one because I see that one upon CXC. A velocity versus time graph with the line of base fit cutting the y-axis. What that mean? Constant deceleration to rest. So you're at rest when you actually touch back when you're there on the x-axis. That's when you are at rest. And a velocity time graph. You're not constant to be at rest if you are anywhere else on it. Am I clear? You're only at rest when you touch the x-axis. If you move off it, if you still before you move off, you're at risk. So you know, climb to no 0 meter per second and no velocity. Am I clear? To no 1 meter per second velocity or no 2 meter per second velocity. Are we clear? So if you're still at 0, you are at rest. Now, umbre up so I travel, let's say I travel 30 meter per second. He start decelerate until he comes to 0. Him stop the car. But he never just stop the car. When continually did. He passed in the opposite direction across the axis. Can you turn around a vehicle per se without momentarily stopping? You have to stop, turn around. We're not talking about drag race. Reverse, stop, reverse. We say we not talk about drag race. Eh? This is not a straight drive road. Are we clear? You mean a one straight line. One straight line. Let me ask you a question. If you have a reverse, you have to stop. Where that man come from, man? Where that man come from? So the brakes have to click on the caliper have to click on the brake pad. For you come to a halt and then turn around and then start repairing. What's up? So you don't stop even in one second. You don't stop. You have to tap for reverse. Are we clear on that? I make bush people tell you we can't drive a vaccine car yet. Ride donkey all day life. A donkey drive come to school this man. You can't sleep. No. As Peanut Dread would say. Constant deceleration to rest, then constant acceleration in the opposite direction. All of this component over here, we are in what quadrant? Quadrant number 1, 2, 3, 4. This is quadrant 4. That means in Ghana one different geographical location. Are we clear? You get where I come from? Sketch of them, you know. So you have to appreciate the quadrant on the Cartesian plane. They represent locations. Go ahead. They have been known to, especially in a multiple choice. Show you what? Yeah, -1, -2, -3, -4. Funny why? Because all that you plot down here, it's like you say. All right, -2 to +3. Get where I come from? And you make that plot. -2 to +4. You make it plot. That's how it was extended down here. No, if you have negative value, you can't use one quadrant. And that's the thing, you know. Look for the follow them where they give a plot. If you have every positive, if everything is positive, do you need quadrant 3, 4? No, you don't need them. You're going to need quadrant 1. That's why majority of the time CXC, we see the entropy 1 year do using using a oscilloscope reading. My word, the graph they mash up the whole of Caribbean year. That was 2018. You see me? Because they give them so negative value, they never know say they put on the second quadrant and go quadrant 2. So they mash up all the people. You get where I come from? Can we sketch this, please? I'm gonna wrap me 15 minutes, you know. I'll take you back. Class has started late. I was here and you stood up on the corridor and chat to people and hug up people and hold on for people and go, you know business. Me tell you if you come to the class long time. So me a thief back in time. At 2:30, I break some taking back the 15 minutes. Tell who you want, call who you want, call no business. I'm taking back my 15 minutes out of your break. Why no fear? Me start, me come here, me there, 15 minutes how long till me get to start. So what? You were on the corridor, I said come in the class. Why me couldn't teach you? Were you there talking with people? And I went for my projector. Was anybody in here ready? No. Nobody here ready. Can we go? Can we sketch? So any bushman when at the exam go mix up velocity versus time graph with displacement versus time graph with speed versus time graph. Diagram your support. Are you clear? Diagram for your support too. Just now when you know this year. Possibility arise, they go want the subject. They're gonna say, crap. Look how me have to spend $40,000 now and how much in night from 5 o'clock to 8 o'clock at night time if you get back the subject. Man, Life is funny. Let's go. Now come let me do it. Me not teach nobody nothing on Friday night. Can we go? Sabbath starts sundown. I'm not teaching nobody nothing on Sabbath. It's not valuable to life. Can we go? Like saving life. Can we go? Next. So here we have more. At rest. What me say about at rest? You see how I look? You see nothing? The object move yet? No, you know move. He still at zero. So you at rest. He now move. You better sketch that. At rest. We have this already: uniform velocity, uniform acceleration, uniform deceleration. Are we clear? Are we clear, guys? You can only have acceleration and deceleration on a. No, me no want to tell no lie. You can only have a straight line linear acceleration and deceleration on a velocity time graph. You can have acceleration and deceleration on a displacement time graph, but how did I know that look? Would it be straight? You can have acceleration and deceleration and have displacement time graph too, but the line now go straight. Wait a go look. Curve. Are we clear? If I display velocity time graph you have, trust me and tell you, when I'm tell you, it's gonna be a straight line. Are we clear? A straight line up or straight line down. Let's go. Can we go? Can we go? Can we go? Go. Go. I told you to have a square yard right now. I'm on line. I understand why it takes so long. What that look curve, sir? What that look curve? None of them are no curve. No, where you drive. Can I go now? I think that's a yes. So here we have non-uniform acceleration. It accelerate, but it not do it at equal values. So it's not basically like 4 meters per second every second. You understand where I come from? Are we clear? Now, first thing, Umbre take on the gas. Then start in change off and 4. Then he floor the gas. So increase by 5 meters per second. And then another 10 meters per second. Another 10 meter, 20 meters per second change. Am I clear? Are we clear? So yes, he's accelerating, but it is not uniform. Am I clear or not? Everybody understand? Can you prove that? How am I going to prove that? I'm going to prove what I just say. Simplex extrapolation. So this, so I'm going to try to divide it equally again. I think about this, so the distance between that and that. Are the distances the same between on the y-axis? No. So what I tell you say? Yes, he might accelerate, he might get more velocity, more and more velocity, he might move faster and faster and faster. But what? It is not at fixed values. Like this is, let's say, 10 on this lesser. And between this lesser, how much? So on this lesser, how much? 10, 30. You get where I come from? And if I go up, it will be even more. Are we clear? You get what I say? So this is non-uniform acceleration, and similar to it is deceleration. And you can put little line on if you want. So let me say, let me put one there. So. All right. Are we seeing something here? Wanna appreciate about this? Let's say if we not pre-life. Proof say that as slow down. As the time increases, he starts to have less and less differences in velocity at each successive time interval. Am I clear? The distance between here is much greater than the distance between here and here. Not distances, but the values between here and here is much greater than between that and that, that and that, and that and that. Are we clear? So Umbre is slowing down, plus a negative, plus its slope negative. Are we clear? Are we good? Now let us focus and then what? Eventually, in the follow If you follow this apart here, you have to come back like that. Yeah. You get where I come from? Until you touch back to zero and you stop. You get what I'm going? Alright, good. So, you're good, you have that? Remember again that the words uniform, constant, and steady mean the same thing. Are we clear? Can I go now? Don't forget, say me I take about 15 minutes. Why rush? Can we go now? I'm glad say people are teaching on no breaks time, even though in visitors. Now, interpreting velocity time graph and speed time graph. On a velocity time graph, you need to know what the regions mean. This is, so sketch this up. Positive, you don't have to put the number if you don't want to. Are we clear? But at least label the axis so you know what kind of graph you are dealing with. Are we clear? So, here, going up, you have what? Positive acceleration. Here we have. Why? Constant what? The velocity is not. So in put first of all, he goes and he go on, and he's continually pressing down, and I can see police, and he say, all right, me obey the speed limit now, and he keep his foot steady, right at 50, right at 8 meters per second. In our probably school zone, right? And he kept on at 8, and he passed the police, and he passed the police. He take him how much minute to pass the police? 1, 2, 3, 4. 4 minutes to pass the police. And he pass the police when do? Probably see one girl we want to talk to, and he's press the brake. He slowed down, and he started to decelerate until he reached the girl foot. One. You get where I come from? So please appreciate that. So anyhow, you see on a velocity time graph, you see one flat line. Are we clear? That's zero acceleration. It also means that the velocity is constant. Please appreciate, right? Just sketch this. Just go zap, 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 zap. Done. Are we clear? Come me tell them say they have right number, man. What are people them love pressure themselves, man? One could sketch off me can just label this, you know. You could have used ruler, that would be helpful. If your hand not straight. Are we finished? You know, some likes you draw this though. I'm glad you draw this. I've got plans for it. Hopefully you draw it accurate. But change your mind, put on back the number. Yeah, but yeah. No worry yourself, no worry yourself, no worry yourself, no worry yourself. Just put on the number then. For one go up to 10 on each axis. Because I forget some for teach you if you calculate the area, the distance where the thing covered. Ooh, look at this. No. Interpreting velocity time graphs and speed time graphs continue. No. Look upon this here. Remember what we said around this up. The how steep the lines is depends how fast the thing will go. Are we clear? The steeper the slope, the more it accelerates, or the more the velocity, or the more faster it will go. Are we clear? So let's go. See the vehicle here. Start. This is a graph showing a motion of a car over a specific amount of time. Are we clear? So 0 minute now moving away, then he start moving. He start to accelerate. It's a short slope. The slope not so steep like that one, yeah. So he was doing what? Accelerating. Then he take on the gas, and then the slope heightens, and what it does? Accelerate. So all of this acceleration, but you need if you can appreciate the differences in that. Am I accelerating slowly? Like mm, like somebody can run inside of your car, or you accelerate very quickly. Are you clear? Then now, yeah, by the time you reach up so you get what? Steady speed, otherwise called constant velocity or steady velocity or constant acceleration. Constant, no, zero acceleration. Are you clear? And here now you slow down. You stop like for between 20 to 50, 20 to 30 minutes. Are you clear? You stop, you now move, you at rest. And then now you speed up in the opposite direction. And then you have a steady speed or velocity in the opposite direction. Are you clear? Because you're literally in another quadrant. Are you clear? You don't need to draw this, but at least you should be able to like appreciate it, given all that you have learned thus far. Are you clear? Because CXC now will be so technical, but I like it because it shows you so much. Now let's go. Hold on for your diagram. Coming to it. Velocity time graphs and speed time graph. The gradient of a speed and velocity time graph represents acceleration. Remember that acceleration can be changed in speed or change in velocity. Are we clear? So, if you go find the gradient of an acceleration time graph, where you get? Where you go get? Acceleration. What is the equation for acceleration? What is super formula say? V for u divided by t. Final velocity subtracted from u initial velocity all over time in second. Now that is it. Now that we substitute and find the acceleration equation B. Why you now memorize the acceleration equation, bush people? Why? Why so lazy? Go ahead and go yam food. Why? Why? I don't know acceleration equation after me teach so much time. Good day. Good day. No. Are we there? Are we there? No, hello. If it is V for u over t, I'm going back over here. So. If it is V for u over t, if acceleration is V for u over t, acceleration A is equal to V for u divided by t, right? You have your initial velocity, your final velocity, subtracted from initial velocity divided by time. No, so if me say me want to find the acceleration that this vehicle had in the first 4 minutes, I would do something like this. Yeah, watch me. Make a big triangle. We use a different color pencil. Make a big triangle. Are you seeing that? Make a big triangle. I say maybe triangle covered right down to my x-axis. Are you seeing that? Don't mix up with the graphic. So that's going to be what? This is going to be me. Y2, or don't say be me. This is going to be me. X1, X2. So basically, no. Which one I think of initial velocity? No more zero. Half is zero because that is started, you know so. One final velocity. So you say this thing will make second. This thing will make sense. Am I clear? So let's go. So therefore, our gradient is going to be equal to, and you agree, and that's why I love physics, the maths, because it actually makes sense. Gradient equal y2, 1y, yeah, if you read it makes sense. If you can't read it, no make no sense. Y2, x2, for x1. Are we clear? So this y2 value represents my initial final velocity. The y1 value down the bottom represents my initial velocity. Initial velocity, when you start with, and the x2 represent the time change, obviously 0 to 4 or 4 minutes, 4 seconds. Are we clear? So initially, where in essence, where I get them? 8 subtract by 0. Let me put in unit them. But like when I use the unit, 8 meters per second subtracted from 0 meters per second all over 4 second minus 0 second. So basically we end up with 8 meter over 4 second. 2 meter per second. So the acceleration meters per second squared. The S them are the same thing, so we add them together. Meters per second squared. Are we clear on that? You have meter per second at top. Oh, you have meters per second at top. You have second at bottom. The two denominator s's will add together and we get s squared. Are we clear? All right, now we good. So we understand how to do that? Do that for your graph. Find the gradient for your paper. Because if this is a record, I would have cried. Subtopic. Determining the area, the distance traveled by the vehicle or a body on a velocity or speed time graph. Velocity versus time graph or a speed versus time graph. So how does one determine, then you finish. How does one determine the total distance traveled by the object? How you do that? Yeah, man, down there. You want to know the distance traveled by the object on the velocity time graph, right? Or on the speed time graph. How we going to do that? We both say. Read that again. Me not think you understand. Remember say you ask me come here. Don't ramp with me. I don't want to see any look of dismay or displeasure upon your face. That's no way you take up. I give you an opportunity for run and you say you want to stay. No. When me say, you find the area under the graph. If you have two square, well, you have to find the area of this two square. If you have one square and a triangle, well, you have to find the area. If you have a trapezium, like you will soon have, we'll have to use the area of a trapezium to solve that. Don't which box? No. Because some box cut in a half, bushman, or quarter. Eh? Yeah, they're right. It's up on two. You can't add them if they cut in a quarter. You can't. It will be so will it be a correct distance then instead of the left out some? If you left out there, will it be a true distance? So remember say, then teacher from grade 2, how we calculate area, sphere, and triangle and this, you know so? And trapezium and whatnot, right? Unless your grade 2 never so hot. Ready? Now here we have a graph. You're going to use your graph, you know. You see, I'm going to teach you. Watch me. All right. So, we have this graph down here. Pay attention on the board. We have this graph right here. This graph is a velocity versus time graph, not true? What we are going to do is we could have also do it to a speed time graph. That show we steady acceleration. That show we steady velocity or zero acceleration. That show we steady deceleration. Are we clear? No. We want to know the distance the object covered. What shall we do? We will split up this graph into any shape, any amount of shape we possibly can split up in. What kind of shape you think you can get out of this? How much triangle can I get? How much, what am I going to get next? Square or rectangle? You sure? All right. Feel one brush wire rub against my skin. So watch me. We split that up. We pop off this up. And we pop off this up. This not poppy right. We poppy good. So let's pop up it. So here we have a triangle, correct? Need to use my ruler. You have to use the ruler free and now go work on the real thing. So this what? Right this up? Right this up? No man, if you think good, you can just on the real thing for the exam. So we end up with this up. We have a triangle this up. We have a triangle this up and we have a square. You sure see a square? Eh? Alright. So what is the area of a triangle? Half base times height. Alright? Is that for a right angle triangle? Or can I use in bush people? All right, so watch me now. Eh? Yo, me not getting. If you excuse me, I'm recording my class. I'm not telling you until I finish. Go and read NA. NA, N, go on N, and then read on. So, or S. I might be wrong, we can't remember. So, watch me now. So, we have, what is the height of the triangle? What is the base length? 2 units. So, basically, so triangle 1, we'll do it by one. Triangle 2.5 base times height. If you try hard enough, you just might get it right. Eh? Eh? 2.8, you sure about that? Don't worry yourself, we are calling it 3. Are you clear? So, the base is what? On the first one? 2. So, it is half, somebody can do it, times 2 times the height, which is what? Obviously, matches to 3. Yes, 3. Alright? For the second triangle, what is base? 2 times 3 are 6, and half are 6 are what? 3. Are you clear? No. Come again. The second triangle over here, so. Eh? What is the base length? Me hear some people say 3 units, some say 4. Who said 3? So you're, yes, so we're going to say yes, so be. 0, 1, 2, 3. So 3 units. So that is half times 3. You know, should I go on for lunch? Whenever I go on. Go on, you know, go on, no man. Right? Half times 3 times. Half times 3 times. What the height? 3 again. So 3 is our 9. Half a 9 hour. 4.5. 4.5. And then for the what? What is this now? You sure it's a square? Or is it a rectangle? Maybe. 0, 1, 2, 3. And then 1, 2, 3. So a square. So that is what? Length squared. Or length times length. Or length squared is equal to, so 3 3s are 9. 9. So that is no. Add them up. So 3 plus 4.5 plus 9 are what? Therefore, distance equal. Find this. Distance equal 9 plus 3 plus 4.5. How much you get? What the unit? What the unit? Since when distance measured in meter per second? Yeah, madman. Meter. Area me a calculate a distance more. Forget the facts of area you use. You all calculate some method for ascertain the distance. So half a meter. My youth no meters person must meter I use my youth no meter. No meter out there so. Meter square that area. However, we never listen to me I said to you. Don't get mixed up. This is a method to determine the distance where the object traveled by finding the area. So if you go CXC meter square, then I'm going to say, well, you don't know where you actually find. Yes, you find the areas, but the area represents the distance. So you have to give them now in a meters. Are we clear? You get that? Half a meter because it represents distance, and that you represent on the graph. So 16.5 meter. Now, does everybody have that in your books? No persons online, please write that off. Thank you. And oh yes, we have a homework for you. You want the homework and then you want write off this first, then get the homework. What do you want? All right. I so want to see what you guys have in your book. So much this would be your homework. Alright? That's your homework. Your homework. So please do this homework. I pray.